Okay. Um, we'll get started just kind of like normal. I'm gonna go through this. I might kind of preface all this stuff with a little bit of notes. But overall, I'm just gonna go over it. You guys can ask questions as I go. If I need to hop on Teams after this, I will. Like, so if you have any other questions that just weren't answered, or whatever, I can always hop on Teams after this. So, um, yeah, I'll just kind of go ahead and start, I guess. First question. This should be one of the easier questions you have. You can do this on a calculator, but like I say in the directions, you need to show your work and then check with the calculator. All right, so you need to actually know the formula for combination. Okay, so if you have NCR, N choose R, this is going to be N factorial over N factorial. Oops, not N. N minus R factorial times R factorial. Okay, so um, this is just going to be 13 factorial over 13 minus 5 factorial times 5 factorial. And when you do this, you get... Also, if you have a calculator, in order to get to the factorial stuff, you hit math and then scroll all the way to the right to probability, and it's there. So I'm just going to simplify this. So you get 1287. Okay, that should be easy. There's not a whole lot to it. It's just knowing the formula, which is this guy up here. Okay. Where we apply that, though, is a little bit different. Okay, so find each term described using the binomial expansion theorem. So you, in some way, you're going to be using what we did in number one, in number two. Okay, but before we do that, the first thing we should do is kind of lay out what each term is going to look like. So we want the fifth term, right? We should know that they're always going to be 1 plus that exponent number of terms, right? So this is a power of 4, so we're going to have 5 terms in this. Our terms are going to look like the first term to the fourth, like with some constant, right? The constant's always going to be 1 to start, plus b to the third times negative 3a to the fourth to the first, and so on and so forth, right? So for our fourth term, we're going to have... Actually, I'll just do this so we see it. Plus b squared, negative 3a to the fourth squared, and then plus b times negative 3a to the fourth cubed. Okay, so, and again, there's constants out in front of each of these. And those constants are going to be, right, so we have 5, we want the fifth term. I want to make sure I wrote this down right. So this will be 4 choose 3. Right, so it's the fourth expansion, right? This tells you the number of the expansion. We want the fifth term, but we're starting at term 0. Okay, so again, if you want to think about we always have a negative 3a to the fourth to the 0. Like this is our technically our first term, but we're starting at 0. So if we're looking at the fourth term or the fifth term, yeah, we're at number 3. I hope that makes sense. That kind of jumbled that. I'm always kind of jumbling it, but we're starting at 0, counting up 4 places, and then that's going to be our second. That's our R, right? So that's what we're looking at. Okay, so if we just do that, 4 choose 3. Again, if you want to do this in a calculator, to get to the combination, you hit math. You go to probability all the way to the right, and then it should be the third option. Type in 4 choose 3, we get 4. So this is going to be 4 times negative 3a to the fourth cubed, which ends up being it's asking for the fifth term. All right, well, this would be for the third term, or for the fourth term. So this would be 4 times negative 27. I'll get the actual correct answer here in a second. So you'd get negative 108 a to the 12th. That would be the fourth term. I'm not sure why I did that. Okay, so this is the fourth term. So I did this wrong. So my bad. We want the fifth term though. So the fifth term would just be b to the 0, negative 3a to the fourth, and then we would have 4 choose 4. Right, 4 choose 4 is just 1, b to the 0 is just 1, and then we have negative 3a to the fourth, which equals negative 3 to the fourth. That's 81. A to the fourth is a to the 16th. And then this is our term. How do I actually plug in numbers for n and r in my calculator? I'm guessing if you have that question, you have a little bit older of a model. So in order to type those in on an older model, you have to type the first term, right, this n first, right? So for this 4C4, right, you'd have to write 4, then go into math, go to probability, find the combination button, hit that, and then just type another 4. And it'll look something like that. It might look like this on your calculator. It's been a while since I've used an older model of it, but that's how it should look. Right, so you type the first number first, then go into your menu, get the combination, and then type your second number. I hope that this makes sense. That was my fault for doing the wrong question first. But we got 2 terms out of it, so hopefully that's 2 examples. The red part is right. The blue part is actually finding the 4th term, which I didn't mean to do. All right. I'm going to move on. I can get more examples of that here in a second, but let's get through this other stuff first. Number 3, evaluate each permutation. Permutation is very similar to combination, right? NPR is just equal to n factorial over n minus r factorial. And then that's it. Okay, so this is going to be 6 factorial over 6 minus 3 factorial, which you can still, I mean, you can use your calculator for this. It's going to be the same kind of process for combination. You hit math, go over to that probability menu, and then you're looking for NPR instead of NCR. and then you're going to type it in the same way. But what you can do, 6 factorial is 1 times 2 times 3 times 4, all the way up to 6. Six minus 3 factorial is just 3 factorial. So you have 1 times 2 times 3. These cancel. So you have 4 times 5 times 6. That's a little bit easier to type into a calculator. Right, 4 times 5 is 20. 20 times 6 is 120. So this should just be 120. Same thing for number 4. This is going to be 7 factorial over 7 minus 6 factorial, which is 7 factorial over 1 factorial, which is just 1. And this is 5040. So 3 and 4 should be easy. Same with number 1. Number 2 is going to be a little bit trickier, but hopefully if we just know that like algorithm, like how each term works, and then what we're actually looking for, it should be straightforward. Number 5 and 6 have to do with arithmetic sequences. And if you remember what an arithmetic sequence is, or if you don't remember what an arithmetic sequence is, it's when you're adding a number, like the same number to each term to get to the next, right? So an arithmetic sequence, it has some common difference, okay? So the difference between terms, right? So the difference between the second term and the first term is going to be equal to the difference between the third term and the second term. It's going to be equal to the fourth term minus the third term, and so on, right? And that's just going to equal one number, which we call D, which is the common difference, okay? So in order to make sure that a sequence is arithmetic, we need to see that the difference between each of these terms is equal. And you should see in number 5 that it's already not, right? To get from 0 to 3, we have to add 3. To get from 3 to 8, we have to add 5. 8 to 15, we have to add 7. Okay, so it does look like it has a pattern, but it's not arithmetic. Okay, so we just are just going to write not arithmetic. Because it's not arithmetic, based on the directions, which in hindsight I probably should have changed, but that's okay. Based on the directions, this is our answer. Okay, so that should be an easier one. Number 6, in order to get from negative 27 to 3, we have to add 30. From 3 to 33, we also have to add 30. From 33 to 63, we also have to add 30. So this looks like an arithmetic sequence with a common difference being equal to 30, right? We're adding 30 to each of the terms to get to the next one. Okay, so that's part 1. Part 2 really should be find the explicit formula, right? And the explicit formula for an arithmetic sequence is n minus 1 times the common difference plus the first term. Okay, that's it, right? So for this would be n minus 1 times 30 plus negative 27. Okay, and we could test this, right? The first term, 1 minus 1 is 0. 0 times 30 is 0. And we're just left with negative 27. Okay, the second term, 2 minus 1 times 30. That's just 30. 30 plus negative 27, that's 3. And we could keep testing it, but this is going to work. Okay, so this is an. right? And you can leave it like this. That's okay. You could expand that out and combine like terms and stuff. I'm not super worried about it. But this is how you get it. That's all I care about. All right. So that's part 2. And then part 3 says to find the 52nd term. So find A52. Right, so we just plug it into that equation, right? So A52 is going to be equal to 52 minus 1 times 30, and then plus a negative 27, so minus 27. So this is going to be equal to 52 minus 1, that's 51, times 30, minus 27. Can you do negative 57 plus 30n? Yeah. So long as that sounds right, that's fine. Again, you can expand this part. I'm not going to. That's just one more place to make a mistake. If you're comfortable with that, go for it. But I'm not expecting it. So for this last part, 51 times 30, that's 1530 minus 27. This is going to be equal to 1503. Right, so 3 parts. Find the common difference, find the equation, find the 52nd term. All right, number 7, the same thing. To get from 30 to 26, we're subtracting 4. 26 to 22, we're also subtracting 4. 22 to 18, we're also subtracting 4. So this is arithmetic, right? It's just we're subtracting a term instead of adding a term. That's the only thing different, right? So our common difference is equal to negative 4. That's part 1, right? It is arithmetic, so it has a common difference. That common difference is negative 4. Part 2 is to find the nth term, right? So it's not the right. So an is going to be equal to n minus 1 times our common difference plus our first term. And again, if you want to simplify this, you can. Both those are fine, right? So you can stop here if you want, but if you want to get down to here, you can. And then the last part is to find the 52nd term. Plug that into a calculator. You get negative 174. All right, so that's arithmetic sequences. Again, if you just know that you're adding the same term over and over again, even if you didn't know these formula really explicitly, you should be able to get there. It might take some time, but you'd be able to get there. All right, so moving on to geometric sequences. First is to determine if the sequence is geometric. And then if it is, find the common ratio. This is like part 1. Then we need to find the 8th term. Actually, it's gonna be part 3. Find the explicit formula. I'd like to do that first. It doesn't really matter. I just like to have an equation before I find a sum term. Right, so that's how I'm going to treat it. Okay, so for this first one, to get from 1 to 6, we multiply by 6. To get from 6 to 36, we multiply by 6. To get from 36 to 216, we also multiply by 6. Okay, so this is a geometric sequence, right? And if you need a reminder, a geometric sequence is a sequence where we're just multiplying some term by the common ratio some number of times, and we're just getting that certain number of terms. Okay, and this is also the nth term. It should be to the n minus 1 because we always have a first term. Okay, so this is going to be our common ratio. That's what we should look at first. Is going to be 6, right? Because to get to each term, we have to multiply the last one by 6. Right? Then our explicit formula, right? So an in this case is going to be our first term times our common ratio to the power of n minus 1. And we should be able to check this. Okay, so if we plug in 1, we get 1 times 6 to the 0, which is just 1, right? That's our first term. A2, this is going to be 1 times 6 to the first, which is just 6. And then we could test it for the third, the fourth, that would work. So arithmetic is adding and geometric is multiplying, and that's the only difference. Yeah, just keep it in mind that they have different nth terms, right? So this is going to be different than this guy up here, right? So they do have different equations, and we just got to be careful about that. But yes, that is the basic difference between both of them. Okay, so that is our nth term, and we need to find the 8th term, right? So A8 is going to be 1 times 6 to the 8 minus 1, so it's just 7. Which is going to be $279,936. Right, so the main thing we need to know here for these geometric ones is that we're multiplying by some number over and over again. That number is called the common ratio, which is what we got here. To find the nth term, we're using this equation, right? So the first term times our common ratio to the n minus 1. And then to find any term in that sequence, we just plug into that equation. All right, so number 9, let's try and do the same kind of logic. To get from 1 to 9 in a common ratio, or sorry, in a geometric sequence, we'd have to multiply by 9. 9 to 25, though, doesn't really work, right? We can't multiply 9 by 9 to get 25. So this is just not arithmetic. Or sorry, not geometric. It's not arithmetic either, but it's definitely not geometric. But just looking at this, right? This is 3 squared, this is 5 squared, this is 7 squared. This is 1 squared. So if we did want to find an explicit formula for this, it'd be something like let's see, 2n minus 1 squared. Just so you're thinking about that way. I'm not going to test you that. You just need to know it's not geometric. All right, so number 10. To get from -1 to -2, we have to multiply by 2. To get from -2 to -4, we have to multiply by 2. -4 to -8, we also have to multiply by 2. Okay, so our common ratio here is 2. And once you get that, so long as you know the formula, everything else should click really, really easily. Right, so our nth term is going to be our first term. Right, that's this guy right there, times our common ratio to the n minus 1 power. And you can check that if you'd like, but it should work. Right, then we want to find the 8th term. So this is going to be negative 1 times 2 to the power of 8 minus 1. So we should get negative 127. Negative 128, sorry. Okay, so those are geometric sequences, 8 and number 10, and that's how you deal with them, right? So find the common ratio, make sure you're multiplying by the same number over and over again, find the nth term, which in that case is that equation to the right. Right, so the first term times the common ratio to the power of n minus 1. So that's all I want you to know for sequences, right? There's summation notation stuff that we went over. I'm not going to expect you to know it for tomorrow. It's good that you saw it and maybe should have put it on the test, but I'm just worried about dealing with sequences right now. Hey, Mr. Sextro. So this next part, this is going to be limits, and this is like really the start of calculus. All right, so this should give you a little bit of a head start in pretty much anything you're doing next year. All right, and I guess before we do this, I'm going to answer these two questions first. So in your own words, what is the limit? I'm not going to write this down because I don't want people to write down exactly what I have for the final. Okay, but a limit is the behavior of a graph at some point. Okay, or at least it's behavior of a graph leading up to some point. Okay, so very early on when I first explained this, when I explained this, I drew a graph. We came from one direction, then we came from the other direction, and where those two, like, quote unquote directions met up, that was our limit. Okay, and that is a limit. Okay, it's the behavior of a graph when you're approaching some point. Okay, so when we evaluate a limit, we're seeing what's happening as we come from the left and come from the right. All right. But for us, we're trying to get to a point where we can just directly substitute. All right. Sometimes, though, that's a lot easier said than done. Right. So if we were to direct substitute our limit into our function, right, we get 3 minus 3 over 9 minus 12 plus 3, which is just going to give you 0 over 0. Okay, so that would not exist. But there is a behavior of the graph at x equals 3. And you can see this if you want to graph it. I'll leave that to you. But there is a behavior here. So what we need to do is we need to get this function to a point where we can actually just direct substitute and get a behavior. Right? So for any limit, there's kind of 3 things that you can do. The first thing is direct substitution, which is where you just plug your limit into the equation, see what you get, and then that's the limit. If that gives you some indeterminate form, right, which is where you get something over 0, then we're going to try and factor something out, right, some discontinuity out. If that doesn't work, we can try rationalizing, which I don't think I have. I'm pretty sure I don't have on this. And if that doesn't work, then chances are you don't actually have a limit at that point. Okay, but those are your 3 things that you can do. All right, so what we need to do is we need to, like, right, we did number 1. Now let's try number 2. Okay, so x minus 3 over x squared minus 4x plus 3. This is going to be equal to x minus 3. and we can factor the bottom into x minus 3 times x times x minus 1. Right, and you should see now that we have a common factor. Right, we can factor those two out, and our actual function that we're dealing with is 1 over x minus 1. And then we can try direct substitution. Right, so the limit as x approaches 3 of 1 over x minus 1 is going to be equal to 1 over 3 minus 1, which is just 1/2. Okay, and we're going to do the same kind of thing for number 12 as well, right? So I'm going to do this in red so I can leave that stuff up there. If we plug -5 into our function, we'd get 0 down bottom. I think. Let's check that. So this would be 25 minus 40. Yeah, so we'd get 0 on the bottom. Okay, so that is trying direct substitution. Now we need to factor something out. Right, so we can try and factor the bottom, and we're going to get -x plus 5 over x plus 5 times x plus 3. We have a common factor, so we're really left with the limit as x approaches -5 of 1 over x plus 3. Right, so then we get 1 over -5 plus 3, which is 1 over -2. Except there's a negative out front. So this is just 1/2. Okay, so those two are actually decently easy, so long as you know how to factor. All right, if you know how to factor, we take out removable discontinuities here and here, and here and here. Once you do that, right, those are just little holes in the graph. So if you disregard those, the behavior of the graph is going to be the same throughout that point. Okay, number 13 is a little bit trickier because there's nothing to factor out, right? So if we just plug in our limit, we'd get 1 over 0, but there's nothing to factor out, right? We can factor the bottom into x plus 3 times x minus 3, but there's no common factor of x plus 3 that we can get rid of that 0. So what we need to do is we need to look at the behavior of the graph, okay? And you can do this one of two ways, right? You can look at the graph like on your calculator. You can actually graph 1 over x squared minus 9, which I will do. Or you can look at the limit as x approaches -3 from the positive end, and the limit as x approaches 3 from the negative end. Okay, and what I mean by that is let's plug in numbers really, really close to -3 from the positive end, so like -2.9. Right, and if we do that, we're going to get some number, right? So if we just plug in -2.9, and then on the left, right, we want to plug in numbers to the left of -3. So we'd plug in 1 over -3.1 squared, and then minus 9. Okay, and what this does is it allows us to kind of quote-unquote look at the graph as we get really, really close to -3. Okay, so if we plug in both of those things, we would get 1 over -0.59, and then we'd get 1 over positive 0.61. Okay, and what I want you to notice here is that our signs are going to be different. And because those signs are different, we know the behavior is different, so this limit does not exist. Okay, so that's like the harder way. The easier way, which I'll bring up Desmos here in a second, is to look at the behavior of the graph and see what happens at -3. Okay, so this is just Desmos graph. You can graph this on a calculator so long as it's typed right. But we're looking at what happens at -3, so right where my mouse is right now. And you should notice that when you come from the right, so when you come from this direction, we're going to go down to negative, and when we come from the left, we're going to go up to positive infinity, right? So the behavior at that point, there's two different behaviors, right? So that limit does not exist. Will you have a question like this on the test? Yes. All right, this is on the practice test. I'm expecting you to be able to at least look at this graph and tell me what happens, which is pretty much taking the limit, right? So as you come from the right, that is different than what happens when you come from the left. Because of that, the limit does not exist. Right? You can do it that way that you did on the graph, that we did on the graph, or you can do it this way that I have on OneNote. Either one, it does not matter. I just want to make sure that we're able to do that. Okay. We already answered number 14. Number 15, what makes a function continuous? What makes a function not continuous? And draw an example of each. Again, I'm not going to answer this right now because I don't want people to just memorize what I say and then write it down. A continuous function is basically a function that does not break anywhere. Okay, so no holes, no asymptotes. Actually, asymptotes are continuous, just on its domain. But there's no breaks in the graph. If there is a break in the graph, it's not going to be continuous at that point. And then what I would like you to do tonight is to think about what each of those things look like. Right? And we went over this in the notes. I gave you a really specific definition, and then we went over a couple of examples of what each of those look like. Right? So be able to talk about both those things, and we'll be fine. Right? And then on to the next part. What is the definition of a derivative? This is something I am expecting you to know and be very, very explicit with how we say it. Right? The definition of a derivative is the derivative of y, so y prime or dy dx. You don't necessarily need each of those parts, but this is going to be equal to the limit, as we can use h to make it easier on ourselves, as h approaches 0 of f of x plus h minus f of x all over h. Right, so this is our definition of a derivative. What does this say? Well, we're taking this slope between 2 points that are infinitely close together. And what that gives us is it gives us an instantaneous rate of change. Right? So we have to use that definition in order to take the derivative of 3x squared plus 4x minus 5 and 1 over 2x plus 2. Okay? So we can just go ahead and do that, right? So the limit as h approaches 0 of 3 times x plus h squared plus 4 times x plus h plus 5 minus 3x squared plus 4x plus 5. Right, where this, where this is f of x plus h, and this is f of x. Right, so we take that all over h, and then we're going to do the same thing that we did in the last couple of limits. Okay, so we can expand, we can cancel out a couple terms, and then see what happens. Right, so 3 times x plus h squared, that's 3x squared plus 6xh plus h squared, and then plus 4x plus 4h plus 5, and then minus 3x squared minus 4x minus 5. Right, we can cancel some things out. 3x squared cancels out negative 3x squared. 4x cancels out negative 4x. Positive 5 cancels out negative 5. And we are left with the limit as h approaches 0 of 6xh plus h squared over h. There should be a plus 4. I thought it was negative 5. It is. You're right. It doesn't change a whole lot, but you're right. They still cancel each other out, bottom line. Okay, so then we have something that looks a lot like what we did the last couple of examples. Okay, so if we plug in h, we get something over 0. So if we factor out an h, we get h times 6x plus h plus 4 all over h. These h's cancel. So then we have the limit as h approaches 0 of 6x plus h plus 4. If we just make h equal to 0, we just get 6x plus 4. And then that is the derivative. Yeah, that should be 3h squared. It's not going to matter a whole lot because it's going to go to 0. But you are right. Yeah, so there should be 3's in front. Okay, but that is the derivative. Okay, so 6x plus 4 is the answer we're looking for. Right, and then next, we'll quickly do number 4. Right, so we want to take the derivative of 1 over 2x plus 2. So that means we want to take the limit as h approaches 0 of 1 over 2x plus h plus 2 minus 1 over 2x plus 2 all over h. Okay, so I think we did this together in class, but I'll go ahead and do it again. We need to combine the two numerators, the two things in the numerator together, right? So I'm going to kind of simplify this a little bit. This is going to be equal to the limit as h approaches 0 of 1 over 2x plus 2h plus 2 minus 1 over 2x plus 2 all over h. Okay, and if we're adding and subtracting fractions, they have to have a common denominator. Okay, so I used the example if we were adding 1/3 plus like 4/7, right? We'd multiply the thing on the right, or the thing on the left by 7 over 7, and the thing on the right by 3 over 3. We're basically going to do that, but with 2x plus 2h plus 2 and 2x plus 2. Okay, so we want to multiply this thing by 2x plus 2 over 2x plus 2, and this thing on the right by 2x plus 2h plus 2 over 2x plus 2h plus 2. All right, and we're going to get the limit as h approaches 0 of 2x plus 2 over 2x plus 2 times 2x plus 2h plus 2 minus 2x plus 2h plus 2 over 2x plus 2 times 2x plus 2h plus 2. And then all of that is going to still be over h. Okay, and again, this looks complicated, but because now that these two things have a common denominator, we can just add their numerators together, right? So then we have 2x plus 2 minus 2x minus 2h plus 2. Okay, so 2x minus 2x, that's just 0. 2 minus 2, that's also just 0. So then we have the limit as h approaches 0 of 2h over 2x plus 2 times 2x plus 2h plus 2 all over h. And whenever we're dividing by something, in this case h, in this case h over 1, we're multiplying by that reciprocal. So then we get the limit as h approaches 0 of 2h over h times 2x plus 2 times 2x plus 2h plus 2. And now we can cancel something out, and then things start to click, right? Cancel out the h's, plug in h is equal to 0 into what remains, and then we have that this is equal to 2 over 2x plus 2 times 2x plus 2 times 0 plus 2, so just 2x plus 2. And then this is our derivative. Okay, so that one is a little bit harder, but I wanted you to be able to kind of apply that limit definition of a derivative to a lot of different things. Okay, so then that is the test, right? So I'm going to leave this open. I'll kind of scroll around, but I want you to kind of think about what questions you have and what questions I can answer right now. Okay, binomial, I can definitely do a couple more of those. And you're still confused on how to set up the two problems at the end. Honestly, the last two problems have to deal with this definition right here. So this one in box red, right? You need to find f of x plus h. You need to subtract f of x and then take all of that over h. And if you can do that and then factor out an h at some point, you're going to get the limit, or you're going to get the derivative. That's really all you're doing. And I think number 3 is probably the easiest thing to see on that. So So hold on a second on the binomial expansion because we're already here. So So really quickly on number 3. All right, 3x squared plus 4x minus 5. Right, we need the limit as h approaches 0. Right, the distance between our 2 points is going to 0 of f of x plus h. Right, f of x plus some distance minus our original point all over h. Okay, so f of x plus h, right, so this is what I did not show. It's going to be 3 times x plus h squared plus 4 times x plus h minus 5. And then you can expand that to be 3x squared plus 6xh plus 3h squared. All right, so that's all that binomial. And then plus 4x plus 4h minus 5. Right, so all of that you see written here is f of x plus h. F of x is still 3x squared plus 4x minus 5. Right, so when we subtract those two, we have f of x plus h, and then we're subtracting just f of x. So minus 3x squared minus 4x plus 5. So we can cancel some stuff. 3x squared minus 3x squared is 0. Minus 4x plus 4x is 0. Minus 5 plus 5 is 0. And we are left with 6xh. There shouldn't be a squared here. Plus 3h squared. And then plus 4h. Right, so we need the limit as this, as h approaches 0 over h, of this over h, right? So then we're just factoring out an h, and then plugging in h is equal to 0, and we get the derivative. Okay, so the setup is really just this definition, right? So, and so long as we're able to find f of x plus h, and then subtract f of x plus h, or sorry, f of x. So long as we're able to find f of x plus h and then subtract f of x and know how to factor and take limits, then you'll be fine and you're able to take a derivative. So the functions basically, yeah. Right, again, we have to find f of x plus h well, right? So what I'm not looking for, right? So some people think f of x plus h in this case is just 3x plus h squared plus 4x minus 5. That is not right. Right? This is. Right, so don't do this. Right, we should be able to do function composition. Right, so there's a lot of canceling and a lot of subtracting, but it's all all of that stuff is stuff that you've done before. The limit part is probably not what you're actually getting tripped up on. Right, so we need to know this definition, and then we need to know how to factor, and really you should be fine after that. Okay, and then to Ben's question, let me grab a couple of examples, and then we can do a couple more, or at least one more. But during that, I'll explain how it works. Okay, hold on. Give me 1 second. Okay, so binomial expansion stuff. Um, Honestly, in my opinion, this is harder than finding the derivative stuff. So at least like there's a lot more to think about when you're taking the binomial expansion. Okay, so the way I introduce this is by finding different expansions of x plus y, right? So x plus y to the 0 just gives you 1. X plus y to the first just gives you 1x plus 1y. X plus y squared, right? If we FOIL that, we get 1x squared plus 2xy plus 1y squared. If we factor in FOIL in another x plus y cubed, or another xy to get x plus y cubed, we get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Okay, and we could do this again. We can multiply by another x plus y to get x plus y to the 4th. We would get 1x to the 4th plus 4x cubed y plus 6x squared y squared plus 4x squared xy cubed. And then plus 1y to the 4th. And we could keep going in this pattern. And the thing that we have to know, right, there are a couple of things to note here. One is the number of terms. Okay, if n is our exponent, let's write this a little bit neater. So if we're talking about x plus y to the nth, the number of terms we have is always going to be n plus 1. Right, so in the 0 expansion, we have 1 term. In the 1 expansion, we have 2 terms. The 2 expansion, we have 3 terms. The 3 expansion, we have 4 terms, and so on. Right? Then, right, we have orders of y that are increasing. And orders of x are decreasing. Right, so we start for the powers of x, right? So let's take the x plus y to the cube, right? We start at 3, and then we're taking 1 off each time, right? And you could also look that there's an x to the 0 here. And then the same thing for y, right? We are increasing each time. Okay, and then we're also starting with a y to the 0. All right, so we should get that. That's foiling in a nutshell. Okay, the big thing here though is that each of these coefficients, right? So the 1, the 4, the 6, the other 4, the 3s, the 1s, all of those are combinations, right? So the coefficient is always going to be equal to n choose r, where r is the number of the term starting at 0. Right, so if we're talking about this 6, right? This is the third term of the fourth expansion, but we remember we always start at 0. So 0 plus 3, sorry, how should I explain this? Right, so this is y to the 0. This is y to the first. This is y squared. Okay, so we're looking for 4 choose 2, right? Because that's the third term, right? So the coefficient here is 4 choose 2, which is going to be equal to 4 factorial over 4 minus 2 factorial times 2 factorial, which just gives us 6. Right, if we were looking for the fourth term here, this would be 4 choose 3. Right, we're looking at this power. So the power of that second term, that second position term, is going to give you that r value. All right, so let me get an example. Right, we need to keep in mind all of this stuff, right? So the number of terms is n plus 1, the order of y increases, the order of x decreases, and then how to find those coefficients. So let me make an example here real quick. Okay, so let's find the third term. Yeah, well, I don't know. Well, okay, so here's a better one. Find the fourth term in the expansion two y plus 4x to the fourth. Okay. So one thing to keep in mind, this x and this y, right? So I'm up here in pink. Those are just positions, right? So when I refer to x, that's the first position. When I refer to y, that's the second position, right? So our x position in this problem is 2y, and our y position in this problem is 4x. Okay, so we want the fourth term in this expansion, all right? So our x term, right, so this term right here, is going to have an exponent of 1, and our y term, right, the second position, is going to have an exponent of 3, because again, our first term is 0, right? So if we were to write these terms out, we would have 2y to the fourth times 4x to the 0, right, times a constant, plus a constant, right? So this would be 4 choose 1. And actually, I'll just write this out. This would be 4 choose 0 times 2y to the fourth times 4x to the 0. The second term would be 4 choose 1 times 2y cubed times 4x to the first plus 4 choose 2 times 2y squared times 4x to the second, and then plus 4 choose 3, 2y to the first, there should be an x in this one, times 4x cubed, and then finally 4 choose 4, 2y to the 0, times 4x to the fourth. Right, so that is the entire expansion. Okay, and I wrote this out really for a couple of reasons. One, so you can see like how the pattern that we described up top works, but also really so that you see that we start at term 0 and we're trying to find the fourth term. So we're trying to find this guy right here. Right, so you don't necessarily have to lay out the entire expansion like I did, but I think it's good that you see that, because that like lets you know how it works. All right, so all we have to do is simplify that box. Right, so 4 choose 3, I'm just going to do this in my head because I think I can do it faster. It's 4 factorial over 1 factorial 3 factorial, which I think is just 4. Yes. 2y to the first is just 2y. And then 4x cubed. 4 times 4 is 16 times 4 is 64 x cubed. All right, so we need to multiply these three things together, and then we get our answer. Hijack height. Right, so our fourth term in this expansion is 4 times 2y times 64x cubed. So 4 times 2 times 64, that's 512. Y, that's just y, and then x cubed. So then this is our fourth term. Okay, so I'm going to leave this up for a second just so you can look at it. But hopefully that clears some things up. Okay, but let me know if it does not. Okay, good. I think I have some examples up here. If I don't have some examples up right this second, I will put a couple of examples for the binomial expansion as well as their answers in that exam review topic. That'll take like 5 minutes. But hopefully that'll give you a little bit more practice. Okay. So while I do that, I'll go ahead and do that now, and then I'll wait for other questions here in a second. I'm going to leave this screen up for a second. I'm going to put those examples into On Campus, and then I'll see if there's any questions left. If there are, I'll stick around and answer them. If there are not, we'll shut it down at that point. Okay, so just give me a couple minutes to put those up, and then I'll see what questions you have. Hi, Jacob. Okay, those examples are up. And then you have a question number 13. So let me see what 13 is. Got it. Okay. So two different ways to do it. And actually, I can kind of explain this a little bit more in depth. So limits have, well, that seems way too simple. Yeah. I guess limits have like two really simple possibilities. They can either exist or not, which sounds like, as I say that, it sounds dumb, but it's true. So hold on. All right. So a limit is what happens as we approach some point. Let's say we're taking the limit at this red hash mark. As we approach that value on the x-axis from both sides. Okay, that is a limit. There are a couple of ways in which that limit does not exist. First is that there are differing behaviors on both sides. Okay, so let's say we have a graph that looks like this. Okay, this graph is not continuous, right? It's broken. But if we were to take the limit at this point right here, right, as we approach from the left, we are approaching this y value. As we approach from the right, we are approaching this y value. Okay, so because there are two different one-sided limits, right, because we have we're getting two different values as we approach from the left and the right, that limit does not exist. Okay, the other way is kind of similar to this, right? We still get, we're still talking about different behavior. We're talking about unbounded different behavior. Okay, so our graph, well, let me start simpler. Right, so say we have a graph that looks like this and like this. And let's say we're taking the limit as we approach this point. Okay, as we approach from the left, right, we're going up until positive infinity. As we approach from the right, we're going down to negative infinity. Okay, those two things are not the same. And because they're not the same, they're different behavior, which means that the limit does not exist. Okay, and then the other one is oscillating behavior. I'm not going to show you that because it's cool to look at, but I'm not going to give you an example like that on the test. But on number 13, all of this work that I did down here is basically what I just said, right? So I'm seeing what happens as we get really close to x equals -3 from the left, which is this part right here, right? So I'm plugging in numbers to the left of -3, and then I'm plugging in numbers to the right of -3, which is, as soon as there we go, which is this part right there. Okay, you can do that. You can also just look at the graph. Okay, and the graph of this is this stuff right here. Okay, so if you just graph this, we're looking at what happens as we approach, in this case, -3. So that's right here. We should be able to see my mouse. think you're able to see my mouse. Yeah. So as we're approaching x equals -3, from the left we're going to positive infinity, and from the right we're going down to negative infinity. Because of that, right, there's different behaviors, so that limit does not exist. Okay, I hope that makes more sense. But bottom line, we're not able to factor out anything, right? It's an essential discontinuity. And there's different behaviors on both sides, so the limit does not exist. Hi, Tommy. Okay. Again, I'm going to leave this on this little part right here, at least for the next minute or so. But if you have questions, let me know. If there are no questions in the next couple minutes, we'll go ahead and stop there. I will be available tomorrow morning too. I have to be there for period 5 to give someone else a retake. So if you do have questions, you can always come in early. I should be there by like 8:30, but I can be there earlier if I need to. Okay, so take a look, kind of think about what I said for number 13, and then we'll go from there. Okay, I'm going to assume that there's no other questions, so I'm going to shut this down. If you have any other questions, again, you can email me. I'll be there tomorrow morning early, again by about 8:30 or 8 o'clock. So if you do have questions, you can always come in then. But I can always try and answer your questions over email too. This should be up, maybe not immediately, but in the next like hour or so. I'm going to copy the link just so people can get it. But I will stop it there, and I will see you guys tomorrow. All right. See you later.